Hello class, I'm Dr. Yang and welcome to cs370 Operating Systems. Now let's talk about the super famous dining philosophers problem. So the situation here is, so you have 5 philosophers named from 0, 1, 2, 3, 4, and you have these 5 chopsticks and they're at the dining table. It's a circular table. Your goal here is all philosophers finish this meal. And the condition here is each philosopher can finish his own meal only when he has 2 chopsticks. And chopsticks are on his left and there's another one on his right. So basically you have to grab 2 chopsticks, one on left, one on right, and only then the philosopher can begin and finish his meal, and then after he finishes, the philosopher can release the chopsticks. And if the chopstick is available, then the philosopher sitting next can grab the chopstick released and work on his meal. All right, so this is the setup. And obviously, this is philosopher and chopsticks are just a metaphor. Philosophers are obviously the threads, independent thread, and chopsticks are resources. Chopstick is usually, you can think of this as a lock. The object that you're going to access is each philosopher's meal, and in order to work on it, you need 2 locks on the left and on the right. So this is the setup. All right, so your goal here is writing or coming up with concurrent algorithm, because philosophers are acting independent with each other. And goal is all philosophers should be able to finish his meal. All right, so the obvious algorithm that you can think of is you can write the algorithm like this. Eat, right? Grab, chopstick, left, and grab, chopstick, right, and then begin and release, chopstick, right, release, chopstick, left. Okay, so this is the sort of a pseudocode. So it's not exactly C code, but you get the idea. And let each philosopher execute this basically the same code. So philosopher 2, when philosopher 2 is following this algorithm, philosopher 2 first tries to grab chopstick number 2 and then chopstick number 1, and after that work on his meal and then release chopstick 1 and release chopstick 2. And all philosophers follows this same rule here. And also, it is important if the philosopher tries to grab a chopstick on his right, and if the chopstick is not available, it's being used by philosopher 1, and philosopher 2 is trying to grab chopstick 1, then philosopher 2 has to wait. And it has to wait while holding this chopstick 2, because the very fact that philosopher 2 tries to grab the chopstick on his right implies that philosopher 2 has obtained chopstick on his left, which is chopstick number 2. And this is obviously lock left and lock right to something, unlock right and unlock left. All right, what could go wrong? So the thing is, this algorithm, this concurrent algorithm, may lead to a deadlock. Okay, and shown here is the deadlocked condition. So as you can see, philosopher 0 successfully obtained chopstick 0 because he obtained the chopstick left, and then tries to grab chopstick 4, which is on his right side. But the thing is, chopstick 4 is held by philosopher 4 for the same reason, and there's a circular waiting pattern formed all the way back to philosopher 0. This can happen because, for example, all 5 philosophers started to eat and all of them successfully grabbed the chopstick on his left. So that means they succeeded in this grab chopstick left code. And then all 5 of them, tries to grab the chopstick on his right, and the thing is, all the chopsticks are gone, right? So they have to wait, and all philosophers are still waiting. This is a deadlock. All right, so let's analyze this situation. So let's take a step back and let's examine the necessary conditions for deadlock. It is important to recognize that the condition here is necessary. That means if you have a deadlock, that means all these conditions exist. So the first one is known as bounded resources. That means in order for deadlock to happen, resources should be limited. So the dining philosopher case, we only have 5 chopsticks. Second condition here is known as no preemption. So if a thread acquires a resource, its ownership cannot be revoked. So all year I talked about the preemptive resources and non-preemptive resources. And the resource here, the chopstick, is non-preemptive resource. Operating system cannot come in and just take it. All right, the third condition is known as wait while holding, also known as multiple independent requests. So what it means here is you have 2 separate independent resource acquisition attempts. This is in contrast with this acquire all, release all semantic that we talked about earlier. So acquire all, we imagined that all the resources can be acquired at the same time in the atomic fashion. No, in this situation, in order for deadlock to happen, there should be independent request. And in this case, in the dining philosopher example, request to grab left chopstick and request to hold right chopstick, they are independent. And also, it's also known as a wait while holding because this second request tries to grab right chopstick, enters into wait state if it's not available, but it enters wait state while holding the left chopstick. Why? Because these are considered independent. All right, the last condition is circular waiting. In order for deadlock to happen, all the deadlock you can trace. Okay, if you follow the graph of all the waiting, then you can create a circular waiting pattern that comes back to you. So there's a set of waiting threads such that each thread is waiting for a resource held by another. All right, let's apply this to dining philosopher problem. So how does dining philosophers meet the necessary condition for deadlock? It's important to know these names, okay, and understand the meaning of this. All right, so how can you modify dining philosophers to prevent deadlock? The first one is the bounded resources, infinite pool of chopsticks. So the thing is, in order to prevent deadlock, notice that this is a necessary condition. That means if you break any of this condition, then you're guaranteed to not have deadlock. So you can prevent deadlock by breaking, any of this. Okay, not all, just one. If you prove it, then your algorithm is good to go. Your algorithm is proven to be deadlock free. So let's examine one by one using this dining philosopher example. So bounded resources. Okay, how do you break this? How do you modify dining philosopher algorithm? Infinite pool of chopsticks. Okay, so this is obvious, but in practice, this is unrealistic because there's no infinite resources. And second condition, no preemption condition. All right, so breaking this no preemption condition implies that you make this chopstick a preemptive resource. So that means you have to come up with an approach or a mechanism that takes away the chopstick from a philosopher if they are in the deadlock. So obviously in practice, that means if the chopstick is a lock, if the lock is held by somebody else, then preemption means that operating system can just unlock it and take the lock from thread. And that's easier said than done. So question mark. All right, the third condition, wait while holding. Remember, this is also known as multiple independent request. So how do you break this? What does it mean by breaking this wait while holding condition? It means that grab both chopsticks at once or neither. I talked about this acquire all, release all semantic. So the solution here amounts to instead of these 2 grab chopstick operation, just come up with an atomic function called grab 2 chopsticks at the same time. So it should be atomic. Okay. You need to come up with this kind of interface. You can imagine it, but again, just like I talked about this acquire all, release all semantic, the question here is how? How do you implement this interface that behaves atomic? So breaking this wait while holding condition implies that you grab both chopsticks at once or neither. I will just say briefly that this how part, can be done. You can implement this thing. The algorithm here is usually retry. Basically, you grab left first, and then if the right is not readily available, then you release the left and then retry grabbing both chopsticks again. So you have to release the partially acquired resource. And most of the atomic operations are constructed like this. You try something step by step, and if you cannot satisfy everything, then you have to roll back. You have to release everything and then retry this whole thing. Okay. All right, so going back to this dining philosophy PowerPoint slide. So last condition is circular chain, circular weighting. And how do you break this circular weighting? You basically modify the algorithm. And one solution to our dining philosopher problem is that if you allow just one philosopher to behave differently, for example, right-handed philosopher, and that actually you can prove that there will be no circular weighting because you basically break the symmetry. And this amounts to that this original algorithm should be used by philosopher 1, 2, 3, 4. They use this algorithm, and eat 0, and essentially the same code, but you reverse the sequence of grabbing the chopstick. Okay, so philosopher 0 has to follow this modified version of eating algorithm. Obviously, everything is the same except the order of chopstick acquisition. And this can solve the problem. And before we talk about the deadlock avoidance algorithm, this right-handed philosopher amounts to the lock ordering approach or lock ranking. It is equivalent. The approach known as lock ranking to this dining philosopher problem results in this one right-handed philosopher solution. And we're going to see it later.